now we are under Roman numeral 3, diamonds, color and optics. We're going to capital D, color. This is a topic we can certainly get carried away with, but we shall try our best not to. Most diamonds are not colorless, like we see here in this picture from Tappert and Tappert. Instead, most of them are light shades of yellows to browns that have less economic value. So let's just say that most are yellows to browns. When the jewelry industry wants a diamond, most of the time we want a colorless diamond. But there are, if faceted correctly, value within these hues. And that introduces us to one of the 4 C's of diamonds, right? Which is the color scale that goes from D through Z. I know we've gone through this a little bit before, but let's take this picture. This is from GIA. This is called a master stone. And most jewelry stores have a master stone reference kit that allows people to check from D through Z, and any diamond that walks in the store, they can try to place them. Now stones that are D, and I don't have all the stones here, but any stone that is D through F, so D, E, and F, these are all colorless, essentially even to the well-trained eye of the jeweler. G through J are going to be colorless to people like us. They are going to be, we call them near colorless, face up. Notice the stones here, these are all upside down. You can see color better when a gemstone is upside down. But so if you're looking to buy an engagement ring, anything up to J is going to be pretty much colorless and good for your bang for your buck, right? Because the thing is that price changes with these letters. In fact, if D is what's sought after, right? So D is kind of the holy grail color. Well, the difference between D and E is actually a 50% increase in price going towards D, or D will be 50% more than E. Now, color matters a lot, but what happens after Z? So J through Z, these are going to be shades where anyone can tell that there's a hint of yellow to it. Well, anything that is more color than Z, we don't have letters for them anymore. Instead, we call them fancy colors. And we'll go through what causes all the fancy colors today. So that's our color scale. Number 2 underneath color is going to be our causes for color. We'll walk through them now. Since most diamonds are shades of yellow, we're going to go ahead and start with yellow. Yellow is produced by nitrogen occurring as an impurity at the ppm level. More nitrogen tends to make stronger colored yellow stones. Sometimes when it's a very faint yellow, well then it's not coveted and it's just part of the scale. But when it's a very saturated yellow color, we call it fancy yellow, and it makes the diamond worth a lot more money. This example is from the Smithsonian, and you can see it there if you ever go to visit. It's called the Shepherd diamond. It's an 18.3 carat fancy yellow, and it was traded to the Smithsonian in exchange for a whole parcel of small diamonds. Basically, when the United States gets smuggled diamonds confiscated by customs, they go to the government and the Smithsonian can decide what to do. Well, they use those in payment for this beautiful diamond. Let's talk about another color of diamond. The color blue is a highly sought after color. It occurs because of a similar reason from boron at the very low ppm level. Nitrogen can occur up to like 3,000 ppm or less, right? So we can say less than or equal to 3,000 ppm. That's not how that symbol goes. The alligator eats the bigger number. Well, for boron, it's like 5 ppm. So it's a very low number. And there cannot be any nitrogen at all. And no nitrogen present. Well, this is a very unusual circumstance because nitrogen is present in very many diamonds, and so blue diamonds are very, very rare. The best famous example of a blue diamond might be called the Heart of the Ocean, and this is where What was her name? She threw it into the ocean at the end of Titanic. Oh, that was a bad joke. That was a fictional one anyways, but it was based on reality, maybe based on the Hope Diamond, which is at the Smithsonian. Or, let me show you a different one since we see the Hope all the time. This diamond I'm going to put up is called the Blue Heart, and it's housed at the Smithsonian as well. Here's a picture of it. It's actually a richer, more saturated blue color, in my more beautiful blue color than the Hope Diamond, even though it's a little smaller. It's a 30.6 carater. And what story do we have here? It was cut in 1910 from a 100-carat rough from the Premier Mine. And one of the interesting things about this Blue Heart is that it's been owned by all the big names in jewelry. Cartier, Harry Winston, Van Cleef, and Arpels, all of them have had their hands on this diamond, but now it's housed in our crown jewels. Next color to get into is going to be green. Green is a weird one. It does not form in the same way. So both of these causes for color, yellow and blue, these were both from trace elements producing color centers. Green and the other colors we're going to talk about are formed in other ways. In fact, I'll put up a picture of a rough green diamond here first, just for space purposes, and then we'll do the notes underneath it. All right, so here's a rough green diamond. It hasn't been faceted yet, but you can see the green color does not pervade all the way through the diamond. Instead, it's restricted to spots. Oh, look at these beautiful trigons on the surface there. All right, so what we're going to do is we're going to go little c, right? We're on little c. And we're going to say green. Green is produced by irradiation. It can be naturally irradiated, or it can be irradiated by man. And what it does is it produces irradiation, produces green skins or spots. We talked about uranium lead decay when we talked about zircon, and uranium goes to decay along, or it goes to a daughter product of lead along a number of decay steps. Well, if you have crystals that are radioactive sitting next to a diamond crystal, some of the alpha particles, so let's say alpha decay, releases radiation. And if we have that radiation going on near diamond, then we can start to bombard the crystal lattice. And we're going to say that the radiation destroys diamond lattice, producing vacancies. And it's these vacancies, I'm going to underline it twice, that are what absorb light to produce the color. So we have color centers with trace elements to make blues and yellows, and we have vacancies to make green. It doesn't have to be uranium lead decay. It can be any other kind of radiation. This just happens to be a common example in crustal rocks. It can also be from groundwaters moving through, but this requires diamonds to be sitting in the crust for long periods of time. So let's even put this down, that this is most common in alluvial diamonds where there is long storage. We need a long time for radiation to damage the lattice. Now, of course, we can do this with reactors and make synthetic green diamonds, but this is how it happens in nature. Now let's move on to our next beautiful colors. And I say beautiful colors, it doesn't have to be only beautiful. The browns, which are not beautiful, pinks, which are stunning, and reds, which are very, very valuable. These are all made in the exact same way, and it is produced by deformation. The mantle is always moving. It's deforming, and if diamond gets caught up in this deformation, you can start to actually strain the lattice. So we're going to say deformation strains the diamond lattice. And what that will do is it changes how the diamond absorbs light, producing anything from browns to pinks to reds. It's unclear which has more deformation and which has less, because one of the weird things about brown, this is the most common color of diamond that's found. But pinks are incredibly rare. But the same color mechanism is produced in both. And it's something that I'm trying to move forward in some of my research to work on. Let me show you some examples of brown diamonds. Here you can see the very nice octahedral. Whoop, get rid of that. Why am I not grabbing? Grab the picture, drive it down. There we go. Okay, and here's an example now of a pink diamond, somewhat rounded by probably some resorption. So the color in both of these are produced in the exact same way by deformation. Now we can, let me show you a faceted variety. I don't have a red picture, right? So let's put up a red. This is one of the more stunning reds that's ever been faceted or found. This again is in the Smithsonian. This is called the De Young red. And if you go to the Smithsonian, please go look at it, because you'll never see a red diamond as spectacular as this unless you are a very lucky person. It's only 5 carats big. Most of the diamonds in the Smithsonian are huge, but because red is so rare, this actually ends up being one of the largest reds on Earth. Well, that is about it for these colors. Let's see, what do we need to do more about it? Some stuff about brown. There was a market, just a couple little bits about brown, is that nowadays we call these, because of marketing genius, because it's the most common diamond that's found, they needed to sell them. How do you sell something that's brown? You don't. But if you call it champagne, that sounds elegant. What if you call it cognac? That's classy. Those are both alcoholics. Baylor, what would we call it? We'd probably call it like Dr. Pepper Brown or sweet tea. That's a joke. Pink, and actually, but this marketing campaign hasn't been highly successful, and it's led to these being sold. Pinks are only coming from one place in the world, essentially, and it's a mine called the Argyle Mine in Australia. They're pulling out pinks and browns from the same place. Oh, what a cool story that could be. Am I petering out at the end? No, you've been petering out the whole time. All right, see you next time.